Hello and welcome to another episode of the book club. We're going to be continuing 2.8 today, and yeah, we'll jump right into it. Okay, so where were we? So we were reading about supporting procedures in computer hardware. That's what section 2.8 is about. We saw the 6 steps that it does. And we talked a little bit about calling conventions. We saw the jump and link instruction and the JALR, jump and link register instruction, and the AUI PC as well. Although I don't know if they mentioned the AUI PC in the book here. I don't think they did. Yeah. And they mentioned, I think the last thing we read was an elaboration where they mentioned that the jump and link instruction can be used to perform an unconditional branch. And let me just go through the margins here. I don't think I've read all the definitions in the margins here. I think the last one I read was procedure. So let's go through the rest of them here. There's the jump and link instruction, which is an instruction that branches to an address and simultaneously saves the address of the following instruction in a register, which is usually x1 in risc-v. There is the return address, which is a link to the calling site that allows a procedure to return to the proper address. In risc-v, it is stored in register x1. Then we have the caller, which is the program that instigates a procedure and provides the necessary parameter values. And then the callee, which is a procedure that executes a series of stored instructions based on parameters provided by the caller and then returns control to the caller. We have the program counter, which is the register containing the address of the instruction in the program being executed. We have the stack, which is a data structure for spilling registers organized as a last in, first out queue. We have the stack pointer, which is a value denoting the most recent allocated address in the stack that shows where registers should be spilled or where old register values can be found. In risc-v, it is register SP or X2. We have push, which is to add an element to the stack, and pop, which is to remove an element from the stack. And I believe we talked about most of that already in the last episode. The stack stuff is what we're just getting into now in the book, but I already covered the stack basically. You can see it there in Milton. I covered it in the last episode. We didn't really talk about pushing or popping, but pushing and popping in risc-v, I don't think they have pseudo instructions for it. Maybe I'm wrong, but I don't think they do. But all you're doing is adjusting the stack pointer, and maybe putting the value of of a register onto the stack, and then adjusting the stack pointer. Or adjusting the stack pointer to make space on the stack and putting a value there. And then popping is you take a value from the stack and put it into a register, and then you move the stack pointer back up to free up that space, right? And again, we talked about my hula hello world, the assembly one. And you can see me doing that sort of thing in there. Did this tweet not go out? I think I maybe forgot to tweet that. Yeah, we started a book club episode here. But do I have the hula stuff open still? That's not it. So let me just open that up here. Oh right, it doesn't, Pelmoon doesn't like GitLab. Okay. Oops, what did I click? Okay, so here's some code. We have the hello world, and I updated this now, so it's actually the one that we wrote on the series and ran on the HiFive Unleashed, which isn't up there right now because I've been trying to get the risc-v PC stuff going, and I think my extension board is bad. One of the LEDs is orange instead of green, which is probably a bad sign, and I can't get to the HiFive Unleashed to see it. And even though, I mean, it powers the HiFive Unleashed, but like the HiFive Unleashed doesn't seem to be like picking it up, the hardware that it's connected to. And then there's also an issue that I'm not able to flash the bit stream to the HiFive Unleashed expansion board, and maybe I'm just doing it wrong because they don't really have good documentation on how you're supposed to do that. Maybe it's because I'm trying to do it from a Windows VM rather than doing it, you know, on a system natively running Windows. I don't know for sure where the problem lies, but I've contacted Microsemi about it, so hopefully they'll get back to me about that soon. But that's why we're doing a book club episode today rather than that, because yeah, I'm kind of, yeah, I tweeted a lot about it on Twitter about what I've been doing, and you can see exactly what's been, you know, going on. Here you can see this LED. It looks like this one isn't lit in the picture, but it is. It's just lighting. This one is like yellow or orange or, you know, some non-green color. And yeah, I feel like that's probably a bad sign. So, and you can see here the flashing, the bit stream failed and stuff. So yeah, I'm having issues, but that's why we're doing a book club. So, oh yeah, I got a little sidetracked there, but yeah, what I was saying is, if you look in here at like the start, you can see an example where I'm doing a pop. So I'm taking the thing that's at the current location of the stack pointer and loading it into A0, and then I'm and you see this is a load word, so that's 4 bytes, right? 32-bit is 4 bytes. And so you see then I'm adding 4 bytes to the stack pointer, and remember the stack grows down, so adding puts the stack pointer higher up, which is freeing up that space. So what we've done with those two instructions is pop a 32-bit integer off the stack, where we popped a word off the stack, and that's the argc that the main function takes. The way it works is when you load up your program, that's what the stack pointer is pointing to. It's pointing to the number of arguments on the stack, And so you load that into the first register, which you pass to. This is the first argument register, right? So you're putting it into the first argument for main. And then you see we also put the stack pointer, not the thing the stack pointer is pointing to, but the pointer itself, into A1, and that's the pointer for argv. And then we align the stack, and then we call main. But yeah, this is an example of doing a pop right here. And like I say, I don't think they have a pseudo instruction for it. If they do, maybe they do and I'm just not aware of it. But that's what a pop is. And a push is similarly, you know, just the opposite of that, right? So there you can see an example of what they're talking about in terms of push and pop. But yeah, let's read about what they have to say here regarding the stack and everything. The title of this little subsection here is using more registers. So suppose a compiler needs more registers for our procedure than the 8 argument registers. Since we must cover our tracks after our mission is complete, any registers needed by the caller must be restored to the values that they contained before the procedure was invoked. This situation is an example in which we need to spill registers to memory, as mentioned in the hardware/software interface section on page 69. The ideal data structure for spilling registers is a stack, a last in, first out queue, where a stack needs a pointer to the most recently allocated address in the stack to show where the next procedure should place the registers to be spilled, or where old register values are found. In risc-v, the stack pointer is register x2, also known by the name SP, which obviously stands for stack pointer. The stack pointer is adjusted by one double word for each register that is saved or restored. And they're saying double word because they're talking about storing the full 64 bits. But of course, you know, you can do whatever word size you want. You can do, because there are load instructions and store instructions for, you know, single bytes, 16 bits values or shorts, and then you have your integers and your longs, or, you know, double word, half word, word. I don't know what the term is for a byte, like you know, a fourth of a word or whatever, but a quarter of a word. But yeah, we have instructions for all of those. So in my example, you saw I was using the 32-bit ones, but if you wanted to do the 64-bit ones, you certainly can. You can work on double words as well. And that's maybe more technically correct, I guess, but so yeah, they say the stack pointer is adjusted by one double word for each register that is saved or restored. And again, like I say, that's assuming that you're using the full 64 bits for the register, which I guess is a reasonable assumption there. It says stacks are so popular that they have their own buzzwords for transferring data to and from the stack. Placing data onto the stack is called a push, and removing data from the stack is called a pop. By historical precedent, stacks grow from higher addresses to lower addresses. This convention means that you push values onto the stack by subtracting from the stack pointer, adding to the stack pointer shrinks the stack, thereby popping values off the stack. We have an example here, compiling a C procedure that doesn't call another procedure. Let's turn the example on page 66 from section 2.2 into a C procedure. So let's just refresh ourselves quickly on section 2.2 what the example on page 66 was. That example was compiling a complex C assignment into risc-v. It was f equals j plus h in parentheses minus I plus j in parentheses. And so we were supposed to compile that. It looks like we were just going down to assembly. We weren't going all the way down to machine code in that example. But yeah, that's what that one was. So this time we're going to be doing it as a procedure. So we have and they're working with double words, so they're using long int in C to refer to a double word. So they say long int leaf example, and long int is the type of the return value. The name of the procedure is leaf example, and then the arguments to the procedure are long int g, long int h, long int I, and long int j. And again, those are just the variables g, h, I, and j from the f equals g plus h minus I plus j, and then f is going to be, the return value from this procedure. So within the procedure, we say long int f, and again, that's going to be what we return from the procedure. And then we say f equals g plus h in parentheses minus I plus j in parentheses. And then finally, we say return f. So that's a straightforward little function there, or procedure, as I said, is the more accurate term, but in the C world, it would typically be called a function. So, if you hear me say function in the context of a C program, think procedure, right? So what is the compiled risc-v assembly code? So just skimming ahead, it looks like they're not going all the way down to assembly, or machine code again. They just want us to reduce it down to assembly. So let me write out what we've got to work with here. And I'm going to use a different convention. I'm just going to call a double word a I64. And of course, in the C language, there are a number of ways to do this. If you use the standard headers, there's a header from the standard library that defines kind of like cross-platform fixed width integer types. So for every platform, an implementation of the C standard library is required to define stuff like int 64t, which is guaranteed to be an integer with 64 bits, or at least 64 bits. I don't know if it's required to be exactly 64. But I feel like it probably is, because they're supposed to be like fixed width types. But anyway, the point is there are types like these that you can get. I think it's in stdint.h or something like that. And then like if you're doing a platform from scratch, then you would do it the same way you would define something like this in the standard library. You just do it yourself. So in the case of you know, like a window, like Windows, you would use long int like they're using in the book, and you just say like typedef i64 as long int, right? Or you could, if you are using the standard library, you could typedef i64 as just int64t, you know. So the point is, you know, you can set things up such that you have a type called i64, and this is what I do in pcalc, for example. I define types like this, and again, you can see this. I don't think I've pulled in the latest, but I did a little bit of cleanup work off stream for pcalc, and I have it in a private repository on GitLab. So I believe you shouldn't be able to access this repository. Only I should be able to access it because it's marked private. But yeah, I have it on GitHub here, and yeah, I just did some little cleanup things. You know, like you can see, I added like maybe inline and global, and you know, just I also cleaned up the way padding is done, and I added some stuff that's like it might have been multiple commits, but I added some other stuff like just some little helpers like for each and for range and stuff like that. But yeah, if we look at the code here, the thing that we're talking about here, you can see the sugar, by the way, for each, for range, global, which just isn't anything. It's purely for, you know, the reader to be able to search for all the uses of global variables. You know, you just stick this in front of a global variable and then you can search for it. It doesn't compile down to anything. Maybe inline is just static inline. We have persistent for a variable marked static inside of a function or inside of a procedure, which is a persistent, you know, variable. It has static storage duration. And I defined a helper size of, which does the casting for me. But you can see how I'm using types like i32, right? And if you, I put these in these model files. So, you know, the libc one, you can see it typedefs all of these integer types to be the ones from std_int.h, right? See, that is providing those types. So it's the job of the C standard library to do the work of making it, you know, cross-platform, defining this for every platform that, you know, the library implementation supports. And then I'm just saying, okay, let's just use those, but I'm going to use my names for them, right? And then in LP64, LP64 is a data model, which means that longs and pointers are 64 bits long, right? So what we're doing there is we're saying, you know, we don't need a long int to be i64. Long on this platform is 64. Whereas on Windows, you would need a different data model because for that platform, long is not 64, it's 32. So you need long, and that's why they use long in the book. But you can see that I'm literally just going through and typedefing them for what they are on my platform, right? On any platform that uses model LP64, the LP64 data model, we will typedef appropriately, right? So that's how you can get types like this, and then you can just, you know, use a nice type name rather than saying long int all over the place, right? So I just wanted to mention that to drive the point home that, you don't need to use the ridiculous standard types. Like if you wanted to be portable without doing like the separation I've talked about of how it's so nice to have a back end and front end separation, what the book is doing is kind of the concept of trying to write code that's portable with the C language that's not depending on a back end or a front end or anything like that. It's just doing whatever you can do in the language to get something that's guaranteed to be 64 bits. And that's what a long int will be, because on LP64, long is going to be 64, but on the, I don't know what it's called, like LLP64 or something, the one that Windows uses, it's still going to give you 64-bit. That's why they're using long in the examples in the book, where I'm saying, we can, in my examples, I'm going to go with this model because this is the way I would actually write it in the real world, and it's something that you can easily do if you do that nice separation between back end and front end, like we've talked about in the past episode. So anyway, we're just, what did they call it? They called it leaf example. And I don't know why they're doing an example of a leaf procedure, but the idea of a leaf is that it's a procedure that doesn't call any other procedures. And I talked about this briefly when we went over the hula code in the last episode as well, which is if you look at if you look at write and exit, you'll see they don't have the prologue and epilogue. And the reason these don't have the prologue and epilogue and stuff is because they don't call other procedures, they're leafs. They do system calls, but these scalls are not the same as a call, a traditional call. These are doing, I think the proper instruction now is ecall. I think scall is the old name for it. It's an environment call. It's an actual instruction. And what it does is, well, in the case of like Linux, it's set up such that it does a context switch, and then the Linux operating system takes over and does a system call. It does some procedure that the operating system has implemented, like writing or exiting the process, right? It'll do some operating specific work, and then it will, context switch back to your process. And that's different from a typical procedure call. So when you're doing that sort of thing, it's not the same as a call, and you don't need to worry about the same kind of considerations that you normally worry about with a call. So you can think of these procedures as being procedures that don't call any other procedures. And as a result of that, you don't need to worry about saving the return address, for example. And these don't rely on anything else that would need the stack. So you can completely omit having a stack frame at all. And you can just have a naked, what's called a naked function or a naked procedure, where you just have the code of the procedure without any prologue or epilogue, right? And that's kind of what we're doing in these examples here. And that's kind of like just a little optimization that you can do when you do this when you have a leaf. If it's not a leaf, of course, you can't do this, because if it's not a leaf, that means you are going to be calling another procedure, which means you're going to need to save the return address at the very least. And if you need to save the return address on the stack, then you're going to need to allocate space on the stack, and then you're also going to need to clean that up when you return from the procedure. So you need a prologue and an epilogue. Right. That's kind of what a leaf is all about, right? Leafs are important kind of for optimization purposes, I guess. I think that's the main reason I know of for caring about the distinction between a leaf and a non-leaf. But anyway, we're taking G, H, I, and J. So we're going to have I64G, I64H, I64I, I64J. And then we have the body of the procedure. So we're going to have a I64, and it's going to be F. And then we're going to have F equals G, what was it? G plus H minus I plus J. And then we're going to return F. And our goal here is to compile this down to risc-v assembly. And like I say, just giving it kind of an informal eyeball, what we can say about this is we know it's a leaf because it doesn't call any other procedures. We need a single variable f. We don't need to worry about saving it to the stack or anything. We can easily fit this in one of the registers, and of course these all fit in registers. So we can use 1, 2, 3, 4, 5 registers. And furthermore, we're going to be returning f. We see that it's the return value. So technically, we could even clobber g, because this is going to work out such, you can see here that one optimization that you can do is, g is only used right here, right? So we can do the g plus h and store that back into the register that's holding g, and then that register becomes what we call f, right? We get rid of g and replace it with f, right? So f becomes g plus h, and then we've lost the original g because we don't need it anymore. And then we do the I plus j and put that in a temporary register, and then finally we do the f minus the temporary, right? And put that back in the f register, and then we just return back to the calling procedure. We can do something like that, just eyeballing it, right? So it's going to be like, add register for f, register for g, register for h, add register for I, or temporary register. I mean, we don't need I and j anymore, so you don't even really need a temporary. You can just overwrite one of these. So you could say like add I, j, and then you could say sub, F, F, I, and then ret, right? Because F is going to be A0. We're going to set it up so that because G is already A0. This is G is A0, H is A1, I is A2, J is A3. You know, and we can reuse these, we can clobber these once we're done with them, which is the optimization I'm talking about. So that's kind of what you could do here. And you can see that, like I say, we don't need to worry about a stack at all. We don't need to worry about allocating space or spilling things over to the stack or anything like that. It's literally just going to be add, and then we're going to add into A0. We're going to add A0, A1. We're going to sub, and it doesn't matter, again, what register we put this in. Let's just put it in A1, the H, because we're not using that anymore either. So we're going to say, you know, let's put this in A1. We're going to do I, which is A0, A1, A2. And then we're adding J, which is going to be A3. And then we say add, or sorry, it's going to be a sub, which is a pseudo instruction for an add. Oh, sorry, I wrote a sub here. This one's supposed to be an add. Right, this is an add. Then we do our sub. A0, and it's going to be A0, A1, and then ret, right? That is leaf example, right? And so you have a label here, and then you just have this code. And then another thing you would do is you'd say dot global and globl. Leaf example, and that just creates the symbol in the object file. So, you know, this code is going to be put into a, you know, an ELF. For example, on Linux, it would be the file format for an executable is an ELF. You know, and that's not just pure instructions, right? That has other kind of metadata associated with it. And the symbols are one of those things, right? So you're putting this in the symbol table, right? Is you're saying we're going to have a symbol for our procedure, right? So, you know, you create the symbol for leaf example, and then here's just the label for leaf example, and then, you know, here's the code for leaf example, right? That's all there is to doing a procedure like this, right? And like I say, this is a naked procedure because it doesn't have the prologue and epilogue, and this is optimized. Of course, you can still have a prologue and epilogue. You can not clobber the argument registers. You can use temporary registers and, you know, stuff like that. This is more of like an optimized example, right? But this is how it can be done, right? So that's what I would do for this. Let's see what the book does. I'm guessing they're not going to do such an optimized version, but we'll see what it does here. So what is the compiled risc-v assembly code? The parameter variables g, h, i, and j correspond to the argument registers x10, x11, x12, and x13, and f corresponds to x20. Now let me see what those are in the calling convention. So I expect, yeah, x10, x11, x12, and x13 are arguments starting at A0, and x20 is one of the saved registers. The saved registers start at x18. So I don't know why they're using x20 again. Like I say, I feel like that's a mistake, but if they're going to put it in x20, what they're going to have to do before the ret is they're going to have to move the x20 into the x10 or a0 before they do the ret, because that's the return value, right? So just keep that in mind. Now let's see what they do. So first thing they're going to do is make room on the stack, because they're going to use the stack to do. Okay, so yeah, so they have the leaf example label. It says the compiled program starts with the label of the procedure, and they have the leaf example label. Then they say the next step is to save the registers used by the procedure. The C assignment statement in the procedure body is identical to the example on page 67, which uses two temporary registers, x5 and x6. And I'm not going to refer back to that and see how they did that in the past, but basically they're just, copying and pasting the code they did before, but they need to save the registers and stuff. So they say they're going to use those two temporary registers, x5 and x6, and they say thus we need to save three registers, x5, x6, and x20. And another thing is, no, you don't. If you're using temporary registers, then you do not need to save them. If you're using, because temporaries are caller saved, right? If you're using saved registers, then you do need to save them. Those are callee saved, right? The whole point of like a temporary register is, you can clobber it, right? The caller needs to assume after a call that the temporaries are gone that were there before. So it's up to the caller to save them if they need them. So no, you do not need to save temporaries, but also you're using the wrong registers anyway, so, but so basically they're going to use saved registers rather than temporaries is the idea. So they're going to need to save them on the stack, and x20 for the variable f is going to be a saved register, so it needs to be saved on the stack before they can use it as well. So they say we push the old values onto the stack by creating space for 3 double words, which is 24 bytes on the stack, and then store them. And, again, in practice, the stack is usually aligned to a 16-byte boundary, so you'd probably actually allocate 32 bytes instead of 24, because, like I say, that's going to be a multiple of 16. But 24 is not, so you'd pad it, right? You'd keep the stack pointer aligned, I believe. But yeah, so they're going to do add-i sp negative 24, which is just subtracting 24 bytes from the stack pointer, which is allocating space for the double words they're going to be using. Then they store double word x5 16 as the offset to the stack pointer, and then store double word x8, x6 with 8 as the offset to the stack pointer, and then finally store double word x20 with 0 as the offset to the stack pointer, right? And you saw this in some of my stuff as well, where is that? Here it is. Okay. So you see how I'm allocating 16 bytes of space here, but I'm storing this word, which is 32 bits or 4 bytes at 12 offset from the stack pointer, right? So what this is doing, right, is you're saying take the value of the stack pointer and add 12 to it, right? Well, adding 12 to it moves you up to we subtracted 16 previously. So if you add 12, that just means from before where you allocated, you know, you're leaving 4 bytes. So like, it'll make more sense if I draw this out. So, you know, let's say here's our stack, right? And so we're gonna allocate 16 bytes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, well, it's gonna be kind of long, but okay, I think if I counted right, this is 16, something like this. Say, you know, we're saying the stack pointer was here, and then you move it down to here, right? 16 bytes down. And then, say, like I say, the stack pointer was here. So above this, we have stuff, right? There's stuff up here, right? And then down here, this is all unused space, right? And so we just move the stack pointer to say we're reserving all of this space right here. All of this space is reserved for us to use, right? And then we're going to say, let's just start taking these four bytes right here, right? This is going to be the stack pointer offset by 12 because the stack pointer is down here. And so then when you add 12, right, this is 12 bytes up from where the stack pointer was. And then you're storing into all of this space, right? You're filling all of this up with your word. So this is where your word lives in memory. And you see, the reason it was an offset of 12 is because that gets you right up to where, you know, the start of where you allocated, right? Because you allocated 16 in total, and, you know, 16 minus 12 is the 4 bytes that you have right here. That's why the offsets are the way that they are, right? That's kind of how the offsets to the stack work. And the other thing you need to consider is if you're allocating a bunch of stuff on the stack, and the stack, you know, when you allocate more stuff on the stack, when the stack pointer moves, if you're referring to, like here we're referring to this as 12, and then as the offset to the stack pointer. But now if we move the stack pointer after that, then the offset is going to change to this, right? And so the offsets are going to change as the stack pointer moves around. And so one thing that you'll often see done is they'll use a different register called the frame pointer. And before you start doing this whole, you know, the whole body of this procedure, before you jump into this procedure here, what you would do is you'd save the stack pointer before you jump into the procedure. You would save the stack pointer to the stack, right? And then you would go into the procedure. And so then whenever you refer to something on the stack, you would refer to it based on the frame pointer, because the frame pointer is going to be consistent, right? It's not going to change throughout the body of the procedure. So whereas the stack pointer is changing as you're moving it around. So sometimes you'll see the concept of a frame pointer. Which is just like the stack pointer. The point is, it's a register that is holding the start of the stack. I think I said you put it on the stack. I meant you take the current point, you know, the current stack pointer where the stack is currently, and you put that in a separate register called the frame pointer, right? And then you refer to where things are on the stack based on the frame pointer, because as you move the stack pointer around, the offset to relative to the frame pointer does not change. The offsets relative to the stack pointer do change if you're allocating or deallocating on the stack, because that means you're moving the stack pointer. And here what we're doing is we have we're referring to a variable on the stack relative to the stack pointer, right? So, here I say it's 12 as the offset, but then if I go and allocate another, allocate more space on the stack and have to move the stack pointer, it's not going to be 12 anymore. So when I go to clean up at the end of the procedure, for example, in the epilogue, if I've moved the stack pointer since then, it's not going to be 12 anymore, and I need to remember that the offset is going to be different, right? So that's something to keep in mind too, that something that you'll commonly see done is the concept of using a frame pointer. And the calling conventions have a register that you can use as the frame pointer. It says you can use the X8, which is also the S0, the first saved register. They say you can alternatively use that as FP, or the frame pointer, right? So that's one thing you'll potentially see being done as well. I just thought I'd mention that right now, because we're talking about in these examples we're referring to variables relative to the stack pointer, and I wanted to point out that caveat that if you're going to move the stack pointer more, the offsets change, right? You need to be aware of that. But yeah, so with our understanding of how you refer to variables on the stack relative to the stack pointer, we see that what they're doing is they allocated 24 bytes of space. So that was subtracting 24 from the stack pointer. And then they pushed the first double word at, an offset of positive 16 from the stack pointer. Because again, they're doing double words, which are 8 bytes or 64 bits. And so, if you take 16, 24 minus 16, 24 is what they allocated. Take away the 16 that you're adding to the stack pointer, and you get the 8 bytes that are at the start of what you allocated, right? And then the next offset is 8 instead of 16, because again, from the last point where, say this is 16 as the offset right here, right? Then another 8 bytes away from that is going to be an offset of positive 8 from the stack pointer, which is down here, right? And then again, to get to the very last of where you allocated, it's going to be an offset of 0. It's just going to be the stack pointer, right? And so, you're just moving up from the stack pointer in multiples of 8, right? That's what they're doing here. So they store to x5, x6, and x20 to 16 plus the stack pointer, 8 plus the stack pointer, and 0 plus the stack pointer, right? Next thing they do is they say figure 2.10 shows the stack before, during, and after the procedure call. The next 3 statements correspond to the body of the procedure, which follows the example on page 67. They add x5, x10, and x11. So that's doing the G plus H, and they're putting that into their saved register x5, which they're calling a temporary. In practice, I would use a temporary rather than a saved register. And also, I would consider clobbering the inputs, because you're not going to be reusing the inputs in this procedure. So you're free to reuse those registers, right? You don't need to grab more registers. You can reuse the registers you've got, right? That's why I did it the way I did in the example. And I'm not saying that's necessarily the best approach, because that can create false data dependencies, which means the if you have a processor that's trying to be very fast and do lots of fancy optimizations, the way it manages registers, it's going to have some kind of extra work to do to try to figure out the fact that these are false data dependencies, right? So that's something to keep in mind. That's one reason you might want to have it be a little bit more greedy with the registers. Hello, GLN2. Thank you for tuning in. And I don't know if, doing it this way or doing it that way, which is better or worse. I'm not saying one is better than the other. I'm just saying, I tend to like the conservative approach where you reuse registries as soon as possible, right? That's kind of the way I tend to approach things. But the book isn't so aggressive with their register allocation. They tend to be more open to using temporaries. One nice thing about risc-v is you do have a lot of registers to work with. So you do kind of have the liberty to use those registers if you so choose. But anyway, so they store G plus H into X5. Then they're going to do an additional add. They're storing X12 and X13 into X6, the addition of those. And that's I plus J. And then they're doing the sub. They're doing sub X20, X5, X6. So they're storing X5 minus X6 into X20, which is what they're doing to represent F. And then finally, they say to return the value of F, we copy it into a parameter register. So they say add I X20 or X10, X20, 0. So they're moving X20 into X10. And again, a move is just a pseudo instruction. Again, you'll see that in my examples, like in the hula code, you'll see I do stuff like move, this MV. That's just a pseudo instruction. I don't know if it's, as the book says, if they do it as an add. I assume the book is probably right about that they just do it as adding 0. Let's check quick with the risc-v reader. So if we look up the move pseudo instruction, it says it is a pseudo instruction. It expands to add I RD RS1 0. So yeah, move is just implemented as adding 0 and storing it in the register you want to move to, right? So the way they did it as an add is the proper way. They just didn't use the pseudo instruction. But that is what the pseudo instruction would expand to. But like I say, I do not know who Christinasa is GLN2, but it seems they're tuned in. Christinasa says, is there a chapter on ultra low power features and techniques? Thank you for your time and effort in making these streams. Let me just check the table of contents, Krish. I don't, and thank you for tuning in, by the way. Let me see here. I'm not sure if they cover ultra low power features, but there is also the other book, Computer Architecture, by the same authors, and we're going to be going over that after we go over this book. If it's not covered in this book, I'd imagine that book might have something to say about it. Let me see here. I'm just skimming through the table of contents really fast here, so I might miss it, but I'm not seeing anything specifically dedicated to talking about low power, but I know it's kind of touched on some. They talked about low power a little bit in terms of, like, there is the power wall, which was 1.7. and they talk about kind of like how to reason about performance, and they mention that that can be not necessarily just performance in terms of like algorithmic performance or efficiency. It can also be like you're optimizing for power, stuff like that. So I think this book maybe touches lightly on it, kind of not as a dedicated section, but just kind of sprinkled throughout. But yeah, that's the best answer I can give you right now. And like I say, the computer architecture book might also have some stuff, some more in-depth stuff on this, but yeah, that's all I know. So I don't know. All right, so continuing what we were reading here. Let me see here. So yeah, I said that we don't really need to use the X20 register like they did. We can just reuse A0 because we don't need to save the G value after we use it here. We're done with G after this point, so we can just reuse A0, right? But yeah, they chose to put it in a temporary registry first. Continuing reading here, they say before returning, we restore the 3 old values of the registers we saved by popping them from the stack. So they do load double word x20 0 as the offset of the stack pointer, then load double word x6 8 offset by the stack pointer offset by 8, and then load double word x5 with 16 as the offset to the stack pointer, and then they do add I sp 24 to free up that space, and then finally the procedure ends with a branch register using the return address. So they say jump and link register x0 0 as the offset, and then x1, which again is just a ret. Ret is the pseudo instruction, and it expands to that. So they branch back to the calling routine. This is actually a really nice example that they did this, an example of a leaf, because I don't know if they're going to talk about it in the book, but the fact that they did an example of a leaf procedure allows me to show you that that can be optimized to not do the prologue and epilogue, where they went through the prologue and epilogue. What I've shown you here is that if you have a leaf like this, you can potentially have a naked procedure where you optimize away the prologue and epilogue, which is what I've done here, right? So that's kind of something that's useful to know about a leaf procedure specifically, where it isn't calling other procedures. It's not something you can always do like this when you're not calling other procedures, because if you take a bunch of arguments, then you are going to spill over to the stack. If more than 8 on risc-v specifically, or more than 8 integers, I mean, or if you're using like structures and stuff, there are situations where you're going to need to use the stack still, and in those cases when you need to use the stack, you can't really get around to the fact that you need the prologue and epilogue to set up the stack and undo that before you return. But yeah, the first prerequisite to having a naked procedure, and one of the most important, is the fact that it needs to be a leaf. It can't call other procedures, because if it calls other procedures, you have to save the return address on the stack. So let's continue here with the book. So it says, In the previous example, we used temporary registers and assumed their old values must be saved and restored. To avoid saving and restoring a register whose value is never used, which might happen with a temporary register, risc-v software separates 19 of the registers into two groups. Okay, so they are actually going to introduce the concept that there are, caller saved and callee saved registers, temporaries and saved registers. So let's see if they have the correct calling conventions for these. The book says X5 through X7 and X28 through X31 are temporary registers that are not preserved by the callee, the called procedure, on a procedure call. Let me check here. X5 through X7 are temporaries, and X28 through X31, so they have that correct. And then X8 through X9 and X18 through X27 are what they said for saved registers. X8, X9, and X18 through X27. So yeah, they do actually have the correct calling conventions in the book, which in my opinion makes it more inexcusable that they didn't follow the correct calling conventions prior to introducing them. I mean, I understand that they had not introduced the calling conventions up to this point, but they had to pick random registers in their examples up to this point. So why they didn't pick the registers that you would use following the proper calling conventions, I don't know. I guess they decided that they didn't need to worry about it because they had not introduced calling conventions up to that point in the book. But I think that's just confusing for people who are trying to follow along and trying to follow the proper calling conventions before being introduced to it formally in the book. Again, it kind of comes back to the complaint I had about section 2.7, where they introduced an example where they needed to do a unconditional jump before they had introduced the proper way to do that, and then they proceeded to do it incorrectly, right? I think what they should have done is they should have introduced calling conventions much earlier in the book. They should have introduced them before doing examples using calling conventions, or they at least should have had a note that calling conventions would be covered later on, which is how you pick which registers they're going to use in the examples, and to just do the correct calling conventions in the examples and say, these are the proper registers following the calling conventions, and we'll explain that later. But instead, what they did in this book is they just picked random registers which do not follow the calling conventions. And I think that's confusing. I think that makes their examples needlessly confusing. So I don't approve of how they approach that in this book. I think they should have, either introduced calling conventions earlier, or at least followed the correct conventions and noted that it would be explained later on. That's my opinion on that. But as we've gone through all the examples, I have been doing the proper calling conventions through all of my working through the examples they give in the book. So if you want to see proper use of calling conventions for the earlier examples before this point, I covered that. But anyway, let's keep reading here. So anyway, the next thing in the book is they have the figure 2.10, which is the values of the stack pointer and the stack before, during, and after the procedure call. It says the stack pointer always points to the top of the stack or the last double word in the stack in this drawing. So I'm not going to bother drawing this out. Basically, what they have is, 3 drawings like what I've been doing when I draw out a stack like this, right? Just, a little vertical box, right? And what they've drawn is 3 of them, and the first one is before the procedure call, and it's just 2 vertical lines and then a blue horizontal line somewhere within the 2 vertical lines. And then it says that's where the stack pointer is, right? There's nothing inside the stack that they've drawn. They've just drawn kind of like, here's where the stack pointer is. It's somewhere, in the stack. And then the next one over, what they've done is they've moved the stack pointer down, and then they have 3 boxes that are contiguous within the stack, like what I've done up here, right? Like they just have 3 of them marked off, 3 double words worth, and they say the first one is the contents of register X5, the next one is the contents of register X6, and then the next one is the contents of X20, and they say the stack pointer is pointing to contents of register X20, right? Which is, like I say, lower down than where the stack pointer was in the previous diagram, right? And the amount that the stack pointer moved down is exactly as much as needed to hold those 3 double words. And then the final diagram is just the same as the first diagram, right? They just moved the stack pointer back up, and there's nothing in the stack anymore. I'll try to show it on webcam, but like I say, I don't feel like I really need to draw this one out. So I know it's not going to show up clearly, but hopefully you get the picture there that it's just, a blank stack, and then they move the stack pointer down and put the stuff in it, and then they move it back up and get rid of the stuff, right? Pretty straightforward stuff. So, and they also marked that the high addresses are at the top and the low addresses are at the bottom. But anyway, moving on here, this simple convention reduces register spilling. In the example above, since the caller does not expect registers X5 and 6 to be preserved across a procedure call, we can drop 2 stores and 2 loads from the code. We still must save and restore X20, since the callee must assume that the caller needs its value. And again, like I said, that's not strictly true. You could optimize away the X20 because you're totally free to clobber the arguments. They're treated like temporaries. They're caller saved. So there's really no reason to need a X20 like they used in that example. The next thing we're going to be covering is nested procedures, but I need to do a short episode today, so I think I'm going to cut it off there, and we'll continue working through 2.8 in the next one. This is actually a really long section. There's still like 3-4 pages more to go. We still need to cover nested procedures, allocating space for new data on the stack, allocating space for new data on the heap, and yeah, that's it. One thing I'll say quickly about what we're going to be covering next, nested procedures just means where you're going to call a procedure from within a procedure, and I've already shown what that entails. It just means that you need to save the return address on the stack, right? I've already shown what that entails. So I don't think there's anything too crazy there, but they go into quite a lot of detail, it looks like, of doing this. So we'll see what they have to say about it. I think they might be overcomplicating it a little bit, I don't know. But after that, allocating space for new data on the stack. It looks like at that point they're going to introduce the concept of the frame pointer, and then allocating space for data on the heap. I don't know what all they're going to cover in that, but Yeah, in the way this is done in practice for like Linux, what you're doing is you're actually there's a system call for this, which is basically the way it's done on Linux is you have the concept of a program break, they call it, which is just like the stack pointer but for the heap. It's like the exact same thing. And then what you do is you use a system call to set the address of the program break. And this can be used to both allocate and deallocate space on the heap in the same way that setting the stack pointer is allocating and deallocating space on the stack. And then from there, more complex allocators are built on top of that primitive. So one thing that's built on top of the system call, the break system call, is usually you have a S break, which instead of taking an address, it's keeping track of where the program break is under the hood, and then you can add or subtract an offset rather than giving it just the address you want the break to point to. You can give it an offset and it will, handle that for you. And then built on top of the break and S break pair, you have things like malloc, which are much more complicated. A general purpose allocator is much more complicated. I mean, if you want to do it naively, it's not that complicated. And I don't think they're going to get into that stuff in the book. And I don't know if I'm going to cover that when we talk about it. We might cover that sort of thing later on. But basically, it's not that complicated if you want to do a naive version of a general purpose allocator. But if you want to get high performance, that kind of thing can get really, really complicated. Yeah, that's all I'm going to say about that for now. So I'm going to wrap the episode up here. We'll continue working through 2.8 in the next episode. Thank you everybody who tuned in today. Nice to see people hanging around, watching, and chatting. That's always nice to see. And thank you also to everyone who watches on the YouTube archive, which is available at risc-v. And you can follow me at HMN_risky on Twitter to get updates about the series. Thank you also to everyone who supports me on Patreon, who really makes the series possible. I don't have any new shoutouts to give today, but yeah, like I say, it just, it really makes the series possible. It's greatly appreciated. And if you would like to support the series and what I do here, you can do so at patreon.risky.tv. I'll see you guys in the next episode, and stay risky, everyone.